Yes. Yeah. Thank you for coming back. I'm aware that, like, the end of last lecture, I was a little fast, but I wanted to get some stuff done related to this, like, anomalies and, like, representation learning and stuff, like things like that. One thing I should actually emphasize is that the things I showed you yesterday were, like, ideas, papers from, I think, the last year or less, right? I mean, so, like, what I try to do is I try to, like, show you basics of classification, and then, like, within, like, one day go to what people really care about in particle physics right now. So, have you got there? Ask me more questions also, or, like, read up, like, find more, like, information in those lecture notes. I keep debugging them while preparing my lecture. I keep debugging my lecture notes and keep updating them on my website. They're currently not on the archive yet. At some point I might put them, but they're on my website. You can download them. Well, since I made it to the cutting edge of research in classification yesterday, we can start something new today and, like, take a big step back and, like, be careful and slow and, oh, there we go. Be careful and be slow about it. Ask a physics question and then think about how we deal with this using machine learning as a tool. Very different, like, we had classification. I mean, I introduced networks. We had classification, like one of the most, or maybe the critical ingredient to any LHC analysis, like asking the question, what is it that we see? Now, that's also a very experimental question if you think about it, right? I don't really care that much. What I care about is, as a theorist, give me a Lagrangian, or, like, some kind of, like way to, like, describe a fundamental model and generate LHC events. For those of you who are not, like, familiar with the, like, the way we divide up the work at LHC, is that theorists start from the Lagrangian and generate events at parton level. For instance, event generation, events that is QQ bar goes to TT bar, top hair production, right? Everybody has seen those Feynman diagrams. There's more of them. There's also, like, PDFs here, and I'm not going to talk about the PDFs, even though these PDFs are, like, as I mentioned, they're, like, the main application of machine learning and LHC physics, called NMPDF. So tell people, like, tell experimentalists, like, how, like, tops would look at the detector. And if you have an especially nice day, we actually even allow those tops to decay, because we notice that unless you have a very boosted top and you do a jet algorithm, you don't actually see the top. You see a decaying top, like, decaying to a B bar and a W. And this one decays to a B and a W, right? And then on an extremely generous day, we decay the Ws side to jets, or maybe to lepton nu, whatever. And that's really the end of it, right? I mean, the rest of the simulation, which, like, involves, like, hadronization and then detector effects, is typically, well, the hadronization is in the heart of, like, a field in between theoretical physics and experimental physics, and then the rest of the simulation, like, what this actually does in the detector is in the hands of experimentalists. So the reason why I'm saying, like, introducing that is because, as a theorist, and I'm a theorist, the first question I think you typically ask is, like, can I use machine learning for these kind of generations, right? I mean, we've been doing these for a long time. That kind of event generation is something that eats a big chunk of the computing budget of the LHC, event generation. So especially when it comes to higher order calculations, precision simulations, it eats a big chunk. So we could try to, like, speed this up and do that, make that better. But you know what? As a theorist, also when you read about a class of networks which are called generative networks, that's just the first thing I think about. So, like, independent of, like, the great motivation, it's always the same. Like, you look, you see something that you can do, and then you always think about the stuff that you know, and then you apply that new recipe to like the problem that you've worked on for a long time, in my case, event generation. Okay, so what are generative networks? Generative networks are just mappings, again, from like, one space to another, but a very specific kind of mapping where you start with variables R. I call them R because they're actually random numbers. And they follow, you know by now that I like my probability distributions, they follow some latent distribution. Latent distribution means it's a distribution in that case that I control. Right? It could be like, uniform or it could be Gaussian, typically a Gaussian. Right? Whenever you see the latent representation, think Gaussian. Right? And you map this onto some network that you call G, for instance, G of R. And G of R should follow another distribution that you want to sample into. And this would be, in that case, the phase space distribution. So this G of R follows a distribution, well, first of all, it's a model distribution that lives in X. X is my phase space, and that should be, if the network is well trained, the same as like, data distribution, where data refers to training data here at X. So what I'm constructing is, again, the network, you can put a theta here or a conditional on theta, are networks where you have a mapping from like, some space here, latent distribution, call it Gaussian, into phase space. And the idea is that we construct it such you can sample it. And that's the new part. The construction of the network is not new, right? The network is going to be the same. It's just like mapping like from R to X. And you have a density here, the probability density here that you have to enforce, and then here you have the data, the density that like, you train from. Right? So the idea is, can I train networks to generate stuff? Yes?
So what exactly is R? You said it's just some random numbers.
Yeah.
Do they have any physical meaning, or literally just pick some random numbers?
Literally just random numbers. Like for those, I mean, if you like, who of you knows Monte Carlo simulation? Monte Carlos? Okay, sorry. So it's essentially the same as like the random number, like that you use for Monte Carlo generation. For like you basically take a random number, like we all just do. It's like a random number. I don't know if you do an integration, a Monte Carlo integration, like it's it lives in a box of 0, 1 in n dimensions, right? Random numbers, and then like originally it's just distributed probably flat, and then you like you use that to like sample your integrand. So it's really just a random number. And it's important that we know that distribution here, because if we map those two distributions onto each other, then like we want to eventually sample from this distribution that we know, right? I mean, you need to know this distribution, because this is how you then actually generate the random numbers to get you the right distribution here. So that has to be something that you can sample from. A Gaussian, yeah, just one thing. A Gaussian is a good idea. Why? Because normally, like random numbers, like have like unlimited, they can have like any real number, right? But if you want these things to be like a little bit compact, so you know where things are happening. And Gaussians are great because Gaussians are essentially compact in the middle, and then they drop real fast. And that kind of is a good like a compromise, like of like cutting off things but still having things smooth. Exponential case, yes. For Monte Carlo integration, you usually start with something that's like flat distributed, and then you like adjust it to get better, right? Remind me, we'll get back in the to this idea in the second half. Like it's something that's easy to like map on Monte Carlo. Yeah, that's my second network I'll discuss today. The first network I want to discuss today is the famous GANs. So they're called Generative Adversarial Networks, GANs. GANs are famous because well, I think they're the coolest network on the planet. So because they're just a great idea. And the great idea is that you use two networks playing against each other to construct this kind of mapping, right? And I'll show you that in a second. So the idea is that you have two networks. One is called the Discriminator Network. A Discriminator network is nothing but a classifier. It's a network that looks at samples from your generated data, following the model distribution, and samples from your training data, following the true distribution, and then it tries to decide what the data that you're looking at is coming from. So to distinguish them, give it a certain sample, and it'll say, okay, that's 80% probability model. Here's something 50% probability model, right? So the discriminator is a trained function, d of x, that works on phase space, and that is essentially, all I know here at this stage is 0 and true, 1 for true, right? And the trick behind the GAN is that you use this kind of discriminator network to tell the generator network, to train the generator network, so tell the generator network, hey, I can distinguish those things here, so you need to do better. So you need to make those two distributions more similar, such that I cannot tell them apart anymore. Let me just draw the structure of such a GAN here on the side, because I'm going to talk more about this. So what the network does is you have a bunch of random numbers, and they run through a generator network here. And the generator network spits out generated events, which are called XG here, right? You also have training data. That could be Monte Carlo, right? Whatever you where you get this from. The training data spits out, we call them XT, the true, the training events. So these are true, and G is generated here, right? Okay, and then you train a network on these two data sets. That's my classifier network, that's my discriminator network. Right? And this network gets trained through a certain loss function, right? I mean, through a look, but and then this discriminator output can be used in the training, hence in the loss function, so loss function of the generator, to train the generator network. The discriminator just trains essentially through its own loss function, independent of the generator. So let me try to write down a generator network that uses a discriminator to get the information if the result is good or not and where it should improve results. Yes? Yes, that is exactly what I'm saying next. But yes. So how do I do that? Let's start with the discriminator. Discriminator is easy because it's a classifier and you know in principle how to do that, right? So discriminator, what's the loss function of the discriminator? Well, if you know these kind of these kind of conditions, what the discriminator should do, I mean, it's fairly easy what you can train this discriminator to on. You can either train it to minimize 1 minus d of x here. So this, you can make that small, or you can push d to 1 here for the data distribution. So that's its truth. For p data, this thing here, if the discriminator is optimally trained, that should be 1. If you sample over p data, 1 minus d should be 0. So that is one of the conditions you can apply in your training, right? You want 1 minus d on data sampled on data to be small. The other thing is you want to enforce this condition. D of x should be small for the model data, for the generated data. Right? These are the two conditions that we will construct our loss function for the discriminator from. like such that we have like these two outcomes for sampling the data, right? We want like d going to 1, so 1 minus d go to 0. For model generated data, we want d to be 0, so expectation value of d of x on the model becomes small, right? Okay, and with these kind of things, I can write my loss, right? So the loss of my discriminator, as let me start with this very simply. So I'm just constructing this part right now, acting on generated and true data. Yeah, I mean, nothing else. I just do that. Now, there's actually one way to improve things a little bit. You can always replace, let's just Taylor series, 1 minus d by minus log d. Turns out that's a good idea. You'll see in a second why that is. It's the same. It's like, that's just Taylor series for small, that's fine. And that's not going to make any difference to to our training objective here, but it's going to make a difference to the form of our loss function, as you see in a second. Okay, so I replace 1 minus d here by minus log d. So minus log d of x on p data. Right, that's the first time on my loss function. And then that one here, I do the same I do the same variable change like from d to the minus log, just with the 1 minus included. So this is a minus log of 1 minus d of x here on p model. And you could in principle introduce a relative weighting of those two, but let's forget this at this point. That should be small and that should be small, so you could introduce a factor lambda here if you want, but we don't have to do this at this stage. Okay, that's my guess, right? Now let's write this out, because you know that I like my loss functions. So does this loss function make any sense from the classification perspective that we talked about earlier? Well, let's write it out and you'll see, right? So this integral dx, it's sampling over those distributions. And the first sampling is over p data, right, here, of x log d of x. The second term here has a relative plus sign, but it's now sampling from p model of x log 1 minus d of x. I'm just writing the definition of these expectation values, but nothing has happened here. Right? Now, if you think about it, we're becoming kind of close to the cross entropy again, right? I mean, this is all starting to look like typical cross entropies again. So let's first see, if I now try to, minimize this thing, I do a derivative here, or with respect to d. So, when does this thing, as a function of d, become small, right? Let's forget, let's assume I can actually do the integrand here. It can minimize the integrand. Then this is, okay, I do the derivative here. Well, p data, let me omit the of x here. Log d derivative is 1 over d, right? Second one is plus p model. Then I have the log of 1 minus d derivative of this is 1 minus d. And then I have the chain rule minus here. Minus, right? Just doing the derivative on that. So that should be 0. Right? I want to minimize that. That's a function of my trained discriminator. Yeah, I call this my d optimal here. That means my d optimal here and this minimum, this is this minimum condition is then, let me just write this down, is p data divided by p data plus p model. I'm skipping one intermediate step. You can do that. Yes, you can do it. Right, so this is just a minimization condition. So I know what my network, my discriminator network will actually learn in terms of when I write down this loss function. I know where it'll end up. This is my discriminator output. Right? So this is not actually the usual p data over p model, the likelihood ratio that we had before, but it's fairly close. And it's just a monotonous function of that, so it's equivalent to the likelihood ratio. So this is our thing is doing, I mean our network's doing fine. Okay, so that's our discriminator, check. Actually, you know what? Let's do a slight layout change here. Okay, now I need to try my generator. So the discriminator will, that's the output of the discriminator. Now, yes?
It's really binary. It's not like a real number between 0 and 1. It's literally 0 or 1.
No, I want this to be 0 for correctly identified generated events and 1 for correctly identified truth events. Of course, the numerical value can be anywhere in between. Unless your thing is perfectly trained, then it will get everything right. We'll try to get everything right. Well, yeah. And then, like, you know, you can, the output is this. Yeah. The output of the discriminator network is, as always, a probability. Right. So you can think of this output to be the probability for being, the training data or truth data. Okay. My generator. What do I do with my generator? Well, my generator just should reproduce with its training d of x equals 0 with the generated data. It should reproduce the correct, like, sample over model. It should get the data distribution right. So my generator will not doesn't want to, like, you know, separate data and model here through this condition, but the generator wants on my model data, so over modeled, it wants 1 minus d to be small or d to be 1 on the model data, right? It wants to get that right. So that's a very simple condition. That's just, like, you know, that's much easier. So I take this 1 minus d, and then I replace the 1 minus d. Remember, I replaced this with minus log d. That was equivalent, d of x. And now on the p model. So the generator will take this discriminator, and it gets that trained discriminator from that training loop here, right? It uses this function d of x and constructs a loss function, all that. If that loss function here, minus log d is the same as 1 minus d, you know, if that returns, like, you know, 1 all the time, then this is minimal, and, like, you know, that means it's true, means it's training data, however, sampled over the model data, so that means you have a perfect agreement between my model data and my training data. Yeah? But, as I said, in terms of for this D, not in terms of some truth information or something. It's trained in terms of the discriminator. The discriminator trains the generator. Yeah. Okay. You can write this, if you want, as a min-max condition here. I can, like, you know, just, like, you know, for notation, doesn't tell us anything extra. Box condition. If you write this as a min-max condition, here they have a minus, no, they have a log d of x p data. I need to get this right because on the blackboard, you know, that, like, you know, we're lacking brain power. 1 minus d of x. But actually, and this one, let's write this as g of r because I want to sample this over model. Model, p model. And I am like this. So I can look at these kind of, like, two loss functions. First, you look at the discriminator loss that's written here, log d of x p data. So this is, am I missing a minus sign? Oh, there's a max for discriminator, so I take the negative of that loss function, which is just written here. That's exactly what I did here, except I replaced x with my function there, g of r, which is, like, you know, the network. For the generator, I have a minimum condition here over the model. Oh, yeah. 1 minus d Oh yeah, we're basically using minus log d. We are approximating this with log of 1 minus d, which around like, you know, that my target value has the same. It's just another Taylor series, I think. I need to write this down. Wrote it somewhere. Yeah. So in any case, this is just a so-called min-max condition. It's just writing these things in a compact manner. I want to stick to the discriminator and the generator loss as is defined here. Okay, that works. I mean, people have tried this a lot. Let's think a little bit like, you know, what happens like with these two losses, generator to discriminator loss, once I actually have trained the discriminator, because that brings us back to a little bit like, you know, our densities, like, you know, what kind of conditions do these densities fulfill? So let me just erase that, like, you know, compact way of writing it, because it's nothing we actually care. So what's the value of the different losses at the optimal point? So optimal point, where I have trained the discriminator optimally, this is like, you know, the distribution I get for d opt, and I can insert this into my different two losses here. Let me start with the discriminator loss again. I just insert that here. That is minus expectation value. That is out of log of d in that position is p data divided by p data plus p model. P plus p model. That's the first term here. And you may check run this right, yes. The second term is here. I pull out the minus. Then I have expectation value log of 1 minus d. 1 minus d is nothing but like, you know, p model plus divided by p data plus p model, right? It's just simple math. Plus p model. Closed. Both of them, like, sampled here. The first thing is sampled over p data. Second one is over p model. Look at these kind of two distributions. If you now go back, that should remind you, each of these terms should remind you of a KL divergence. So these are really, just think of it modulo, like, you know, like in the KL divergence you have p data over p model, or this is a KL divergence of the two hypotheses, namely p data or p data plus p model, and that's a KL divergence of p model, second argument p data plus p model. So this is just minus the sum of two KL divergences. Now, I told you about the weakness of the KL divergence, namely that you sample over either p data over p model, which, you know, means like, you know, you can like, you know, get some instabilities. It might not like, you know, cover the entire phase space very well. This combination is much better because you have two KL divergences. You want both of them to be small, right? But you have one sample over data and one sample over model, which means now you really have to get like the distributions the same. So p data modulo factors of 2, p data and p data plus p model has to be the same, which just means nothing that p data and p model have to agree, but sample over p data, and then p model and p data have to agree sample over p model. This thing is just a definition minus twice. This is called a Jensen-Shannon divergence, and it's really just defined that way of p data, p model. So what we have is we have a discriminator that in terms of our like, you know, underlying probability distributions, it minimizes the Jensen-Shannon divergence for p data and p model. That's just the definition of this divergence. And this is really think of it as an advanced scale divergence. So this is, if you think about it, same thing as we did before. Slightly different in the sense like, you know, it's more stable. It's actually a better way of doing it than just writing the KL divergence because, you know, it has these two terms and they both have to vanish independently. And it's a discriminator that comes out is fine, like, you know. So we have trained ourselves here a little better discriminator than we had originally. But the idea is the same. I am still thinking about minus signs, but like, you know, we do this by the end of the lecture. Okay. Generator. Yes?
I'm right? And you minimize, so you get this optimal gain.
Yep.
So what you got over there is just the value at the minimum after
Yes.
the training.
Yes.
So why do we care to diverge? We said we want our loss function to be of this KL or JS divergences in order to optimize it, but this is after optimization already.
Yeah, and this is the behavior that is true here, but this is also the behavior of this loss function around the optimal point then, because this is like how it scales. So if you're not quite perfect, this is like, this is your endpoint of your training. Like, this is like, actually the endpoint is just the minimum value. It should be very, very small. But, this minimum value is, the loss function should go to 0, ideally, right? If everything is perfect. But if you have like, distributions, you can look for like the behavior of the loss function around the smallest value. Oh, I'm missing here, there's a factor because of the definition of the Jensen-Shannon divergence, because the factors 2 and 2, here 2 and 2 are missing. Strictly speaking, oops, there's another term plus 2 log 2. Like, not that we care about it. Remember, in the loss function, we always ignore constants, but like, now it becomes 0. So this is the behavior around the perfectly learned like model in terms of those densities. But that's not super surprising in a way, like this is how we constructed it, right? I mean, I just wanted to take the opportunity to introducing the Jensen-Shannon divergence at this stage. Okay, what's more interesting is the generator loss, because now that we haven't talked about. So my generator loss, where do I write this? Let me start. Let's squeeze this here. So the generator loss here at that point with this perfectly trained discriminator, that is the expectation value of log. And it's the same, right? Remember that like the generator loss is the same as the first term of the discriminator loss, just with a different sampling. So this is the log of the, here, 1 minus d opt. Oh, no, actually, I wanted to write, sorry, I want to do this transformation here. That is, before I do that, minus d, sorry, of x. That's the form I had in this min-max condition here, p model, because that makes it easier. So if you do that transformation here, then I have a log of 1 minus d. Log 1 minus d is the same thing here, second term, so I know this is the p model divided by p data plus p model. Expectation value, and then the generator samples over p model. Right, that's what the generator does. So that's what we get here. I'm ignoring factors of 2, constant factors, because we don't care about them. If you think about this now, the generator, it only has one of these terms, so it's not a Jensen-Shannon divergence, but you think like, this, you can write this out. This is p model as integral dx, p model of x log p model divided p data plus p model, right? So this is nothing but KL divergence of, and now I have to be a little bit careful. No, well, it's actually fine, p model. And here, the second function is p data plus p model. If you write it like this, it's just like, that. Now, I told you that I don't care about like, factors which don't depend on anything. So if I introduce a factor 2 here, which is nothing adding like, a loss term that's constant, then I get that. And this is a little easier to read. So the generator loss function around the perfectly trained discriminator ensures that my model distribution and the average of the data in the model agree using a KL divergence. Right? So again, using like probability distributions, we have 2 learning conditions. One, the classic discriminator, now written in terms of the Jensen-Shannon divergence, and that's new. The generator loss is new. The generator loss is the KL divergence between the model distribution and the average of the model and the data. That works the same as the model and the data, obviously, right? I mean, this is just shifting things a little bit. So what the generator wants you to do is just like, get a model distribution that agrees with the data distribution. It's as simple. Now, nicely written in terms of all our densities. So, yeah. What if everything is perfect? If everything is perfect, that's called a so-called Nash Equilibrium. Nash Equilibrium is if those two conditions find a solution that, solves both of them at the same time. It's not that one wins over the other, but both of them actually manage to together converge on their two minima. The Nash Equilibrium is given by P model equals P data. Right? Obviously, this is you get everything right. So this thing vanishes here, and that thing vanishes. And strictly speaking, if you take all the finite terms into account, then the discriminator loss here becomes 2 log 2. And if you do this factor 1/2 right here, then the generator loss goes to minus log 2. Just finite values. Not 0, but finite values. So that is the definition of these generative adversarial networks. The general adversarial networks have two loss functions. They have one discriminator loss. The discriminator loss here ensures that your network D tells apart generated and true or data. So it tells apart data that comes from P data and data that comes from P model. And then you have the generator that uses that D. The only way the generator talks to the data is through. There's no direct line here. The only way the generator talks to the data is using this discriminator output as a function of X. And the generator output is just here, the log 1 minus D, but sample over the model. That's the only thing the generator can do, right? It samples over the model and uses that input. And if both of them agree to be happy at the end of the day, you get that condition. Of course, in this kind of competition, it's entirely possible that one of them wins and the other loses, in which the loss function for the discriminator approaches its minimum very fast, and then the loss function of the generator basically gives up, or the other way around. Things like that, right? That's going to happen. So we have to the training of these networks that lead to an equilibrium of two independent trainings. You have to be a little bit careful, that they actually converge to the right solution and not a solution that basically solves one of the problems and not the other. Yes.
So the advantage with respect to actually telling the generator this is generated, this is true, because this you can do, and this would be a perfect discriminator.
Yes.
The advantage is that you can check whether you're going to.
Yes. The advantage is that the network will always, the generator will always invest extra training time where it needs to be invested, because this is where D is not well trained. Or where D actually tells a visible difference. So well-trained D tells a visible difference, and so the generator notices, okay, something is wrong here, and then I will need to work on that. Whereas if you were trained this on true versus false, labeled data, the other the generative networks are very autoencoders, variation autoencoders you can sample from. They optimize distributions, right? But they don't they don't get guided to the point where, to the regions where it hurts, and this is what the discriminator does. We'll see another another useful feature of those discriminators later. Yes. It's okay, but it's not truth labels. It's labeled by the discriminator.
The truth is, are you actually data or are you generated?
Yeah. So the labeling here goes not from G and T. These are labeled data sets, right? You don't feed them into the generator loss. You feed them through the discriminator network into the generator loss. So.
You label for the network D, you label the XDs with a 1 and the XGs with a 0.
These you label for the discriminator. And the generator does not see those labels. That's the important part. The generator doesn't see the labels. The generator only sees, how good am I in the first certain phase space region as judged by the discriminator. So they're fighting each other. So the discriminator is trying to be smarter than the generator, telling it, okay, here, and then the generator said, okay, but if you can tell these things apart here, I should work on my network, then generate a new generated data. No, you cannot tell them apart. That's the game. Yeah? Yes?
How does the distribution of the initial seeds, like the R's, come into play? Like what you feed into
the generator, the R's, whenever you generate data, right, with you have random numbers, and they're outside. They're just Gaussian random numbers. They go into the generator. They produce the generated data. You train a discriminator. Everything works. You change the loss function. The generator changes, takes another set of random numbers, generates a new set of G. So these random numbers, if you want, they're just random Gaussian numbers. Nothing happens to them. They just get
How do you, if it's not Gaussian, it's some different distribution for the R's, how would that come into play?
you can run the same thing with other random number distributions. You just need to make sure it's always the same. It's you can sample from them. You can do this with you can do that with uniform distribution. But remember, uniform distribution weights live in an unlimited real axis, right? So whenever you have random numbers which come uniform, they have corners and edges. Where things are not, you can do a derivative, and there's always instabilities. So you can use any distribution you want here. You can sample multimodal if you want, whatever you want. Just it has to, that stays the same. That doesn't get changed during the training. So you train the generator always as a network to take random numbers of a given form and produce XG. Oh, so what we typically do is the number of I didn't talk about this. So good question. So what we do is we take our random number vector, the same dimensionality of the phase space that we know here. That is a very physics application if you think about it. Normally when you look at images, right, the dimensionality of your representation data is huge, right? Images, and there's far fewer features. When you do event generation here, I know exactly what my dimensionality is, so I can do this reduction of dimensionality that we do by hand. So good question. We choose the random numbers to be as small as possible, and as small as possible is the dimensionality of the phase space I want to fill with the independent degrees of freedom. Yeah, that's Rn. You can make it bigger if you want. Not smaller, then you correlate stuff that you don't want to correlate. Yes?
How do I tell my generative network what is the Lagrangian of my theory?
You don't. You train this. The Lagrangian enters, in that case, just through the training data. The thing is trained on data, on generated data from MudGraph or from Sherpa, or actual data, anything you want. So this is just, at this stage, this is just an additional piece in addition to the event generation.
Did you say in the beginning we want to have some, for example, BSM model and we generate events?
Yeah.
And we have the data don't know.
It's a little bit stupid. Standard model Lagrangian enters here through the data. I need to actually, my data form input data for these events. Or BSM, or whatever you want. This thing is trained on events to generate other events. Right? Now you can ask, is this useful? Simple question, simple answer. Imagine you have this is actually a little bit of an unsolved problem. So you have imagine I have a million TD bar events, right? Why would I want to train a network on a million TD bar events? How would I gain? There's a whole lot of ways you can gain. For instance, it's much cheaper to ship a network than a million TD bar events and so on and so forth. And you can unwrap them in any short amount of time. There's been a long discussion on the gains of that, because the question is, if I have 1 million data points that I train on, how many can I actually generate before I kind of overtrain, overtrain, or how many events can I generate until the limiting factor in my generated data is the statistical uncertainty on the 1 million events that I trained on. This is a question where, in principle, the answer is very clear. Think of fits. We're doing fits, right? Imagine you have a fit that you know the function, like, whatever, simple function, Gaussian or something like that. You need, what, 3 data points to, like, determine the underlying function? How many data points can you then, like, sample from the Gaussian that you have just fitted to this data? A whole lot, right? So clearly there is a gain. These things, like, we know already that networks are nothing but, like, non-parametric fits. So there will be a gain. How big that gain is, play with it. Open question. Nobody has been able to sort this out quantitatively. But we have, like, people have done studies. We have done studies. People have done studies, but it's an open question. Yes.
Don't I then, if I don't put in any advantage but just the data, don't I, per definition, overtrain my network? If there's any BSM signal, the generator will also learn this, and I will just think this is kind of background and stuff.
No, wait, I think it's a misunderstanding. What we are doing is we are taking a data set, and a generative network will take that data set, learn the features in that data set, and that data set can be, like, theoretically generated, and then just reproduce these these features with an entirely new data set that you sample here from these random numbers. So this is what you generate is a new data set that has the same learned features as your training data set that the network has learned. That's the job of the discriminator. And then it generates new data. That new data is statistically completely independent from the original training data, but feature-wise, it should reproduce it.
Okay, I think I get it. So data doesn't necessarily mean measured electricity data. I can put in any simulated model, whatever I want.
You can simulation, actual data, any combination, whatever you want. Modified data, shifted data, anything you want. So this is, like, what you can play with. I just wanted to show you that we can, like, do these kind of, that we can do this, use neural networks to generate something. Just one important aspect here is, some of you must have seen this, like, these machine learning tools where you put in a postcard or, like, a photo, and then it, like, gives you that photo in the style of Van Gogh or something like that, right? Right? So this is, like, you change in the context of a known picture, right? This is not a generative network. This is a network that just changes, like, the representation a little bit. So in other words, you have to separate this. Like, what I'm trying to do here is I'm trying to take a network that produces new paintings in the style of Van Gogh, not sampling on, like, one photo, but sampling on random numbers. Yeah? So this is, like, that's, like, that's a new thing. Like, this network will generate stuff that nobody has seen before. There's actually an art application to that is, like, Van Gogh, like, so where you use a network and it actually makes new paintings. I mean, you train it on, like, big data sets of paintings, and it makes a new one. And it's not in the style of our thing. Like, this is generically new. The events that we are generating here are a little bit more boring than Van Gogh paintings, but, like, these are new. These are, we are sampling. It's important. There was a question. Yeah.
Slightly technical question in terms of the actual utilization. So what you said before in terms of finding the minimum of the loss function of the D and also of the G, is it like doing step by step in the gradient descent?
Yes, gradient. Yes, yes. It's gradient descent, just regular training of two networks. You know that the discriminator training is a regular discriminator, it's just a classifier training. The generator training, like, the way I wrote it down here with the loss function, you see it's totally equivalent. What you now do is, alternatingly. One, then the other, then back and forth. And then you see, if you notice that one of them is winning and the other is giving up, you give this other one a little bit more time. So, like, you might want to schedule this a little bit or check what's coming out, such that you enter this, like, double minimum of the two loss functions.
Essentially one company, if you do it, it's essentially one complicated loss function. Right? If you do it step by step, because they affect each other.
Exactly.
So it's like a big function.
So the way I think of it is, like, you have, like, two losses. Discriminator generator, right? And what you want is, like, there's some landscape here, but you want to be here. Like this is like essentially not the 0, 0, but like the corresponding. So like, somehow through this landscape, you need to find a smooth way to end up here, right? But, if like, things don't work well, your network might decide, okay, I go here, and that's just fine. And that's, you don't want that, right? So you have to, like, adjust your path.
If these are both one-dimensional function, you have a two-dimensional function.
Yeah.
It's a different, more
Yeah.
complicated function.
Yeah, but it's important that, like, yes, you train them. Like, you train the discriminator, then you need the trained discriminator to train the generator, right? Change the generator, produce new data, retrain the discriminator. Discriminator gets trained, new discriminator, better discriminator, again, tells the generator, like, something about its generated data. Generator says, okay, doing better, but not quite there. Changes, produces new generated data, going into the discriminator again, discriminator training. So it's really alternatingly.
No, I'm saying that when we did that in mathematical analysis here, you just took the derivative with respect to the loss function of the discriminator. You're not guaranteed to find that, right? If you don't find this origin,
Yes.
so you're not guaranteed to be in this optimal position. This optimal is only in terms of the loss function of the discriminator. But you didn't take the gradient here of the two functions, you just took the derivative of this function. So
Yeah.
if you're optimizing together, so you're not, you understand what I'm saying?
No.
You're not guaranteed to be on the LD equals 0 line, and then you have the D optimal.
No, you're not going on one line and then optimizing the other. So like,
That's exactly what I'm saying.
yeah, you have to find a nice path. And finding that nice path and like keeping the network from like taking that turn, you might have to adjust a little bit of the training. So like, sometimes the generator training is a little harder, so you give the generator more time to train, for instance, right? Training a generator is always harder than training a discriminator. So like that we know, general rule of thumb. And so like the generator will need more time than the discriminator, for instance. So you need the balance. And this is by means not trivial at all. Like that there is actually a balance that goes into the right thing. Yes?
So you say it's not clear how much can be gained, but how much has been gained?
So we have played with like toy examples, like Gaussians. It very much depends on, okay, the main limitation in like learning these densities in any classical way and doing stuff is the dimensionality, it's cost of dimensionality, right? So the higher your dimensionality is, the bigger the gain from a good interpolation will become, right? If you take a stupid interpolation or a good interpolation, like, you can combine this, like, high dimensionality like will always benefit the networks. So the key factor is like, like what's the dimensionality, for instance. But I mean, these kind of like, gain factors, in the literature, like machine learning literature, is like a place where like, they, you can read about them is gaming, right? Because you look at gaming and like, you have these beautiful, like, in your gaming, your screens, you have these beautiful pictures. And like, you look at them and there's no way that like this entire data could have come through your cable to like, at that rate, right? I mean, that's impossible. This is like, way too good, right? So there, you typically have a generative network that like, makes like a reasonable picture into a really nice picture, like, and so these are these gain factors. It's called amplification. Check it out in the literature. It's an open question. It's a long-standing discussion. It depends on the application. And to me, this is one of the open questions. I don't know. I don't know how many. I mean, for events, I know the gain factor is a couple. I'd like it to be 100, but it's probably not 100. I don't know. Like, you're asking, like, I'm just saying, like, here's an open question, solve it. If you solve it, like, we like you a lot. Yeah? So it's like, no. And we don't know. We don't know the answer. There is a gain. Some people dispute that there could be a gain, but this is obviously, you look at the fits and there is a gain. But the question is how big it is. OK. That was one network. And like, I can just show you like, like one distribution. I don't want to do this like in glorious detail, but I can show you one distribution for TT bar. What did we typically do here? You generate TT bar events, and then you plot a kinematic distribution. Like, for instance, this is here, like, like you want to look at this on your phone. That's going to be on page 72. So this is a PT distribution here of, like the top, for instance, reconstructed from these 3 particle momenta. And like, like any PT distribution, all look the same, you know. You have seen one PT distribution, you have seen them all, right? So this is how they look. This is just a PT distribution. Now you can actually look at the model over data or GAN over truth. Take the ratio of the two binwise, right? Here, and that is, well, here's 1. And what you see is that things here are pretty good, and at some point things get worse. There might be even a bias, like, you know. That's a very typical behavior of this kind of curve. So you look at that and say, like, yeah, I totally understand why that is, right? Because I got lots of training data here, which means I can learn the density really well. And then the fact that the curve is coming down here just means I also got less training data because my training data is exactly distributed along this curve, and then it gets worse here, right? And yeah, and so like there might be even a little bit of a bias, like, you know, and it's certainly not in agreement, but that's like, you know, it starts being noisy and then there starts to be a bias. Okay, you see that? You show that to my friends, Sherpa friends in Göttingen, and they said, okay, thank you very much, we're not interested. I mean, like, first answer, thank you, like, you know, but we are like physicists, we're not machine learning people, and that might look good to somebody who thinks about machine learning recipes, but that's not good enough for a physicist. Which brings me back to the first lecture, and that is, yeah, no, an error bar would be nice, right? Because, you know, if I had an error bar, a Monte Carlo simulation is also not particularly good in details. However, you know, like, you know, the uncertainty on it is just like, you know, like from your Monte Carlo distribution, the statistics. So here, it's not. Well, this is a network. I mean, I don't know nothing, right? So this is, okay. So big question, people, machine learning people, give me a network that gives me error bars. And if you think about error bars, this is a little bit of an unorthodox introduction to the next kind of network that I want to discuss. If you think about error bars, what we have here is a function that maps random numbers to phase-space distributions, right? Okay, now, what is this error bar going to be on? Well, if you think about it, what all of these networks do, and this is also how we derive them, you know, they approximate a data distribution over phase space with a model distribution over phase space. And from that, roughly like from this training, like, you know, procedure here, I also know in principle what the error bar should be, right? The error bar would basically be, say, I have a distribution here, P model of the phase space. This is just a probability distribution over phase space. And if that underlying probability density can come with an uncertainty, then I know for every phase space region what my uncertainty in the underlying density is. And this generated data here, well, that's nothing but sampling according to a P model, right? And that means I could say, in this phase space position, where I just threw an event now, right? My uncertainty on the underlying density is 10%. So I could, for instance, say I have an event. If I assume the event has an event rate 1, that event has 10% uncertainty on its event rate 1. But here out in the tail, the phase space densities are like, you know, much less well known. So the network would report here's an event, but I'm really not very sure about the underlying density because I'm lacking training statistics. So the uncertainty on the underlying density is 50% or 80%, big, right? So this is the philosophy that we'll use to do now these generative networks with uncertainties. So I want for every phase space point here, I want an error bar on the density. So I want to learn two things. I want to learn an underlying density, that's P model of X. So I want the density, P model of X. Oh, I got P model of X. And I want the uncertainty on it. Call that sigma of X. That's what I learned, right? So that's my task. Now, if you think about generative models in principle here, you could say, okay, my model maps random numbers onto X, right? If I have an uncertainty on that, I can, well, I mean, it is here, but since these are just mappings, it could also be here. And the moment, like, like I train a network now, I need to decide, okay, like what do I want? Like, do I want something that a deviation from the Gaussian here, or do I want to use a deviation from the actual phase-space distribution? In principle, they should be equivalent, but they're probably not, because in practice they're not, and the mapping is very, very complicated. And as a matter of fact, I don't even know if they're good or not, because I don't know this mapping. I can't control it. So what do I want instead? What I want instead is, I want a different kind of network. I don't want a GAN. I don't want this mapping. I want a mapping where I have full, right? Where I have full control over that mapping. I want a mapping where I can say, well, I can do the errors here. I can also do the uncertainties here. And because I can map between these two distributions back and forth, and maybe I know the Jacobian, it's all well defined. It doesn't matter. Define it here, all good. Right? So this is like one of the many motivations to switch to, where did I have them? To switch to machine learning generative networks that are not like a one-dimensional mapping, but which are bijective. So what you want is, you want a network that goes that. Because if you do this like back and forth, I'll write this again in a second. If you do like a network that does this like back and forth, well then it doesn't matter. Then you can actually do that job. So what you want is, let me erase that, like write this slightly nicer and define my G's and stuff properly. So that's still my problem here. But I want a network that starts from a latent distribution, my random numbers, P latent. And it maps that on phase-space distribution X P data, or P model. That should be the same. That's the training perspective. OK. And now I have two directions of that. I call this here G theta. If you go this direction here, it goes G theta of R. And this one here is, I call that G bar. That's the inverse direction, G bar of X. So I want a function that's bijective between the two of them. All right. So question is, can I do that? Can I like train a network? Can I build a network that works bijectively? And if you're like, I'm not going to go into the machine learning details, but the answer is yes. All you need is, you need a nice, like, in a structure where, like, obviously bijective now, R has to be the same dimensionality as the phase space, right? Because it's bijective. So you want just a bunch of layers, right, that you can actually evaluate in one direction or the other direction. That's my R space here, and it's my X space. Yeah. And these networks are called normalizing flows. The person who taught me about them calls them INNs, invertible neural networks. That's Uli Köther, machine learning guy in Heidelberg. Invertible INNs. I like that because it kind of captures why I want them. Other people might want them for different. I want them invertible. These layers here, just technically, I will not talk about them at all, how they're constructed. They're called coupling layers for whatever reason. Just a technical term. And there's different ways. Like, there's a whole different level, there's a whole literature on coupling layers, how you can construct these, and I don't want to get into those because I think the gain is very technical, and also the technological development on those has not ended. So, like, I don't want to be too detailed on it. What instead I want to say, okay, now if I write, going back to my distributions. So what I want is, I want a network where I can express, like, the integrand here, dx p model of x. Now this is given theta here onto dr. Like, this is just infinitesimal over phase space dr p latent of r. I need that kind of relation, because that relation you can now solve. P latent of R. You can solve this for P latent of R. Okay, I can say that like this. Okay. So in Heidelberg, like when you do this, you divide by D's, right? I always call this Jekyll's rule that I do that. This is because Jörg Jekyll, my colleague, spends like lectures and lectures and lectures teaching people that you should never ever do that. Like should not do this, ever like divide by D. And then like you teach your undergrads that like Jekyll's rule tells you that you can almost always do that, except in the cases where you cannot. And if you're actually willing to like give or take a factor -1, then you could do it more often than like if you're not. So like this is just like yeah. Okay. And this latent distribution dx by dr, x is defined here. X is g of r. So this is like just the Jacobian, and now we actually get to write this dg of r divided by dr p model of x given theta. That's more one way of writing it. P latent, just let me check I have everything here. Yeah. Oh, wait. X is g of r theta, okay? The other way around, you can do the same thing. P model now of x given theta. I need these two formulas later. Is P latent and P latent of r, but r is g bar of x, like this here, times the Jacobian, which in that case is dg bar of x by dx Jacobian. Okay, in my invertible network, the great advantage that I have in my invertible network is that I can relate the two densities now through a Jacobian, which is known, which we didn't do before, right? Through a Jacobian, and either this direction where latent distribution is like, in terms of this Jacobian here between x and r, but then I introduce my definition of my network is either given like this, like latent distribution is dg by dr Jacobian times p model, or p model distribution is p latent times the Jacobian g bar dg bar by dx. And g and g bar are defined as these two mappings. And these two mappings, G and G bar, are expressed in the same network. It's just like it's one invertible network that ideally that you can pipe through like one direction or the other. Yeah? And how I build this, as I told you, I build this like through a series of very smart choices how to define these layers. The key is again like the same thing we did before. The key to this kind of this layer structure is again to find building blocks which as a building block are invertible, and then you stack them. It's the same argument, like has nothing to do with with like your brain cells or something like that. And you want standardized building blocks where each building block shifts a distribution. I mean, like sometimes you find in the literature these plots where this is a Gaussian and this is something like this, right? And then each building blocks does something a slight change, right? So like, this is just a linear, like slightly like the redo layers we had before. So like you transform the densities through those building blocks slightly, a little bit more, a little bit more, a little bit more, until you have like the mapping from the Gaussian distribution here to a phase-space distribution, and from the phase-space to the Gaussian, right? So think of this as like epsilon times like 1 over epsilon changes. Yeah, and as I said. Want to talk about it, don't want to talk about it.
The ReLU, for example, wouldn't be invertible.
No, the standard ReLU stuff, that's not invertible. So you need others. Yeah. As a matter of fact, you cannot do this like one. Typically, these are not scalar. These coupling layers are typically defined in a high-dimensional phase space, high-dimensional space. So like the simplest, they call affine coupling layers. You can only do in 2 dimensions, and you play games with like triangular matrices and stuff like that. You can read it. It's like in the notes. It's in 1 million reviews, and yeah. Okay. Now imagine I have this network. I have this network, and this is what I want this network to do. Same thing that I always do. Okay, let's think about a smart loss function then. So what's my smart loss function? How do I train such a network? Well, I train my network. We come back to my favorite loss function, always the same. through likelihood loss. You know, I mean, if nothing else, like go for likelihood loss. Like you have no other good idea. Like, you know, some people might go for MSE. Like that's not. Don't. If nothing else, go for likelihood loss. I showed you yesterday, like, you know, that probability loss is also very, very cool, but if nothing else, likelihood loss. Okay, so what's that likelihood, or log likelihood, is what you want is the model distribution over x given theta, and you take the log likelihood, and that whole thing sampled over p data. You want that to be minimal. Think KL divergence, right? Always the same thing. This is like, you know, we have seen that loss before, right? So you want the model samples over data. You want this, the training samples over data. You want sample over training, over the training data. You want this p model of x and theta to be minimal. If you wanted to do a log likelihood ratio, you would actually divide this by p data of x, then you have the proper likelihood ratio. Everything is like, you know, well-defined and normalized, except that, well, log p data over sample over p data doesn't include the model. So this is this extra the constant term that I like forgot, like threw away in the first lecture as well, right? So this is nothing but a likelihood loss. Okay. Now, what can I do with that? Well, I can use that way to rewrite it, this distribution. So I can write instead, because of the structure of my model is G, so I need to somehow get G in there, like I take that. So this is a log here, P latent of G bar of X, right? Let me indicate here G theta, that's the network function, right? And then I have the second term here. This is a times here, but then I'm under the log plus the log of, well, this is Jacobian here, dg bar of x, or dg bar of x dx. Jacobian here, closed p data. That's how it looks, right? Now we have two terms again. Like, so what do they do? Like, you know, I minimize, this is my loss. This is my likelihood loss. What I want to, like, you know, the g theta is missing here. Well, I train my network. If you take that direction, only my network g bar, defined here as going from data to latent space. That's one of the directions I can evaluate it. So I train that. So what do the two things do? Well, to this term here, yeah, I mean, that actually, that tests the latent distribution, right? So you have the p latent of g bar of x. And like, you know, that thing ensures that on the latent side, which is now, remember, for g bar as your target side, you get the right distribution, right? This is a Gaussian, for instance, right? So this here becomes like a term that, like, you know, well, I mean, this log of a Gaussian distribution in g bar, that's going to be a chi-squared eventually, right? When this is how they look. The log of a Gaussian is chi-squared, right? So that you can do. And the second one here is, that's the log of like the determined g bar of x by dx. That's what actually trains, like, you know, your network. If you think about it, like, you know, this is like, you know, just like, you know, on the data. So minimizing that logarithm, that's the actual, like, you know, mapping from one space to the other. So you have two terms that you train, one guaranteeing, like, you know, that the end comes out right, like, you know, and if you train g bar, the end product is the latent distribution here, because you sample from the other side, you go backwards, and this here is where you adjust the network. This is Jacobian, which is really cool because this is the Jacobian is known everywhere, right? So okay, this is Jacobian, and that's known, right? It's actually known, and not only known, you can evaluate at every single point. You know that the Jacobian is there. It's in your network. Right? I mean, in your coding, in your training. Okay, good. Exactly what I mean.
You cannot derive it and get to your coding. You just have g bar. You can evaluate it.
That's what I mean. You can numerically evaluate the Jacobian at every point x, because that's nothing what the loss does. So the Jacobian is known. Numerically, I mean, it's not, I mean, the network is G. Like, you know, but this Jacobian here is what you construct in your loss function. You can compute it. Right? And yeah, this is like, you know, the very brief introduction into these networks. And you can use them. Okay, fine. You can do TD bar. And the plots, I showed you, like, you know, it's going to be the same kind of event generation. You can plot the same distribution, the same thing we did for GANs, you can do with this kind of network. Yes?
So how do you get G?
G is the mapping. G is...
What you get here is G bar, right? G bar is the function that you train on eventually. After you did
Oh, yeah. Oh, sorry. No, sorry. Yeah, sorry. Your network setup is such that it is symmetric, so it's like every coupling layer is bijective. So if you have G bar, you have G. You can every function, like, you know, numerically, this thing is symmetric. You can go from here to here, you can go from here to here. So once you have G bar, you have G. That's the important, like, you know, thing. You can evaluate, or in other words, these networks can be evaluated ideally in both directions the same speed. So you can go from here to here or from here to here. Both directions. This is, if you look into it, training is actually going this direction. Like if you look into this, right? I mean, like, you know, we are sampling the data here, and then we go in this direction. Exactly. And you sample taking the Gaussian in the other direction. So you better be fast in both directions. You want this network to be fast in the training direction and in the sampling direction.
All that is in the structure, it's not the loss function. Because what we did before with the
No, this is...
before, if we can run it the other way, we also have the
No.
function of the...
No, yeah, this one here, in the structure, it is invertible. Again, this normal generator is not invertible.
Yeah, but it's invertible because of whatever structure.
Yes, the coupling, yes. Yes. Not because of the loss function. No. It's not, the loss function is not the reason why it's invertible. It's a structure that's invertible, and the loss function is making use of it, in the sense that you train it in one direction and you run in the other. The loss function is just like, you know, what you want to do. The structure here that I didn't talk about is... So, just one fast thing, because I promised that. Like, how do I do uncertainties on that? How do I do an uncertainty on G? Well, I mean, this is actually fairly easy. So Bayesian of that version is... Let me like, you know, recall from last time what we did for the Bayesian network. So Bayesian network, BNN, we call this, is had, like, you know, if you did look at this, like, this was the likelihood loss P model of x given theta, sampled in theta following the distribution Q. And then we have the second term of the loss function, which was the regularization, or the, like, you know, the prior term Q of theta, P of theta. This is just, like, you know, the old loss function that we had from the Bayesian network, right? I mean, just copied from the first lesson. If you think about this, you know, I can trivially do this, right? I mean, here, making that Bayesian in terms of the loss function, it's super simple, because remember, the non-Bayesian of the version of that was just the likelihood loss. That term didn't exist. The Bayesianization of this network was sample over, like, theta here, following the distribution and putting the prior in. I can do the same thing. I just, like, add another layer of sampling over theta, put the prior term in, and I'll be fine. So I can use the Bayesian INN. And you can write this down here. That is nothing but log P latent of G bar of x plus log, then here, G bar of x del x, Jacobian, sampled over P data, and another sampling step over theta, right? Plus some kind of regularization term, which is, well, I mean, there's nothing different. It's just high-dimensional Q versus Gaussian prior. So if you think about it, once I ask the question right, like once I have these normalizing flow networks, making them Bayesian networks is very, very simple. But I think for particle physics applications, that's actually a big step. Before, I mean, okay, the first thing, if you go, I don't even want to go into this in detail, but if you now look at a typical distribution, phase-space distribution, what you'll find, we're doing this TD bar, right? The typical distribution that I drew like a minute ago, what actually comes out if you use that, like we have a little bit of an advertising plot, figure 52, is now you have a distribution of some kind. And allow here, so it's like this is some PT to the top, whatever, pick whatever you want. That distribution. Now this is here the Bayesian INN over truth or training data. That's the one here. And what you find is that, like, the Bayesian INN is good, and, like, the central value of the network might do the same that the GAN does, right? I mean, it's like, it is at some point training, like, it starts to wiggle around and then it starts to deviate. What's important is that this network, in addition to having this central value, it gives you an error bar. And says, well, here, this density is sigma. My phase-space density here in the tails. The uncertainty on that phase-space density, right, is sizable. This is like, okay, this is like, literally, if you apply numbers here, like 1.2, 0.8, whatever, something like this, right? So the density, the uncertainty on the density here, like, integrated over everything, goes up from 5% to 10% to 20%. This is the information you're using here. And then you can just, you can plot your generated events with an uncertainty. Which is something like, that I think makes physicists happy, makes me happy, because, I can actually control this. What made me even happier is the last thing I want to show you about these networks, because, I'm a pheno guy, right? So you get your error bars, you're a happy person, right? Like, for pheno people, pheno physicists, having a prediction with the error bar in a generative network is nice. Like, it's what you wanted to do. Like, I should say, like, we worked a long time on these networks with the uncertainties. That was my plan when I wrote, like, thought about, like, put the first graduate student on generative networks. My original plan was to do this with uncertainties. We use GANs. So we learned a lot about GANs, including that you cannot actually assign uncertainties because you cannot control the bloody Jacobian. And then you ask the right people, and then you, like, learn that there are these other tools which also work much better, but they also allow you to do uncertainties. But something that I think is funny is that, like, then you start working with them. Yeah, let's keep that. You start working with them, and you do a little toy model. Let me show you something that is kind of cute. So imagine you want to learn a function. Imagine you want to learn a function, and for technical reasons, as I told you, the INNs with these, like, coupling layers can only be defined in 2 or more dimensions. So let me, like, learn a function which is linear in one direction and trivially constant in the other direction, a ramp, linear ramp, right? 2-dimensional square, linear ramp, 0 to 1. This was our toy model for our Bayesian network. That we, like, the Bayesian INN that we wrote. And you look at that, and, well, what the network comes out with. So if this is, like, the truth distribution is just here from 0 to 1 or 1/2, whatever. So that is truth. What does the Bayesian network do? The Bayesian network gives you a perfectly fine estimation of that. Something like this, and gives you an error bar around it. And this is all fine. All looks good. Then you tell your student, Marco, why don't you plot the error? I want to see how the error behaves as a function of that thing. So, like, this is the density, let's call it P, now called sigma. Plot the error. Marco comes back, gives me that function, 0 to 1. Right? Has a minimum here at roughly 1/2. So, okay, you look at this and you say, well, from all I know here, from my physics intuition, like, oh, by the way, this should also go up here. You have lots of data here, error is small, little data here, error is big, uncertainty is big. So that is clearly wrong. Like, no way that can be true, just wrong. So Marco goes back, codes a lot, like debugs, whatever, doesn't find anything, comes back, like, it's like, no, I think it's right. I said, like, no, but it can't be right, it's wrong. So then at some point you think, okay, maybe my intuition is wrong. So what do I really think? When I say my uncertainties in regions with with large amounts of training data, I learn well, and with regions with small amounts of training data, I learn not as well. The underlying assumption I'm making is that this network is kind of patch-wise learning things. So it's learning locally. It's learning something here about the regions from that training data about the regions with low phase space densities, and something here about the phase space regions with lots of training data, but only from the regions of large training data. So patch-wise learning, right? And then this is not possible. If that was true, then you would have a small uncertainty here and a large uncertainty. No, a large uncertainty here and a small uncertainty here. So that can't be true. So thought about it, but let's go back. What I said in the first lecture, I said, these things are just fits. Is it possible to understand this kind of behavior? And it's actually not that hard to understand. So imagine my density is linear, right? Now let me assume that I fit a curve that's ax plus b to this to data here, right? But I know p is a density, so that the network only knows about the density. So my normalizing condition is dx p of x. The integral is 1, and that's a squared half plus b, which means nothing that my function that I'm actually fitting is a times x, then a here times, right, the squared should be there. They're plus 1/2. No, oops. I bring this to the other side. B is minus 1/2, so x minus 1/2, and we need this minus later. Plus the 1. That's the function you fit, right? Now you do error propagation. You're looking at delta p as a function of delta a. And while this is very simple, this is delta p is delta a times x minus 1/2. As a matter of fact, well, error propagation has to be positive because it's in squares. So delta p squared is delta a squared times x minus 1/2. So now you look at that and you say, hey, I do get a minimum. That is actually from this, if I understand my network as a fit, which I told you in the first lecture it is, then that's actually totally expected. Because what the network does is not learning patch-wise. What these INNs do, and I have no idea what GANs do, but what these INNs do is, they shape curves around, right? From here to moving over. So they shape these curves, and this is really just they're finding a class of functions, and then they're effectively fitting those parameters. And effectively fitting those parameters means that, you can have this kind of error propagation, and that the uncertainty actually has a minimum at 1/2. So sometimes when you start asking a very fino question, when you go into the networks, all of a sudden you get a nice result because asking a fino question, getting an uncertainty, and then noticing that a network learns an uncertainty together with a density, and the two of them track each other, right? Yeah. Then you can learn what the network learns. So how does it? So yeah. So an INN is really just a fit, if you think about it, right? If you look at this, that's the only explanation I have. I mean, somebody might have another, that's the only explanation I have for this kind of behavior for the Bayesian networks. So that, I think, is pretty nice because, there are days when as a pheno guy, you think you found something that's actually a little bit more fundamentally interesting. With that, I'm done with the generative networks. If you want to learn more about it, read in the lecture notes. I mean, generative networks, especially these INNs, I told you my motivation for using them was that we can control the uncertainties, and we can actually define uncertainties, and then we can control the uncertainties. It's not that hard to do, if you think about it. All you need is to write the correct definition of the uncertainties, namely that should be uncertainty on the underlying density you have learned. And then you need the right loss function And the INN has exactly the right loss function to Bayesianize it trivially. And then we'll talk more about another use of these normalizing flow networks and INNs tomorrow. Thanks. Okay. Yeah, death.
Okay, so that's the
Tomorrow. Good. Thank you.